Welcome to a lesson with Dr. Powell. Let's take a look at what happens when we have a vector field, take its curl, and then take the divergence of that curl. So, first of all, since we're taking divergence in a triple integral, that would be equal to the surface integral of just what happened before we took the divergence. Now, the surface integral of that encloses a volume, so it's completely wraps around and enclosed. Let's split it up into two surfaces, a surface right here and a surface that has a border, a curve. So let's let this curve divide the surface up into two parts, so S2 and S1. So we naturally can just add those integrals together, S1 and S2, and that should be equal to the volume integral. Now, each one of these then would be equal to the line integral, but in different directions, because if you're on this surface, the line integral is going one way, and then the other surface it's going the other way. From one side it looks counterclockwise, from the other one it looks clockwise. That just means that these are just the negatives of each other, or opposite signs. So when we add them, we just end up getting 0. Now notice that this whole process showed us that the volume right here of this was equal to 0. And that's true, actually, no matter what volume we pick. It didn't matter which three-dimensional volume we picked, every single one. Narrowing down on a point here, everywhere. The only way for that to ever happen, so every single volume gives you that, is for this vector field right in here, this guy, the divergence of the curl. I guess it's a scalar here if you're just thinking of dx, dy, dz, or you could think of it as a one-dimensional vector perhaps, but that's fine. So, but as a scalar, thinking of it that way, the only way for that to happen is for that to be exactly equal to 0, which tells us something. So if you take the divergence of the curl, you end up getting 0. Thanks for watching.